the last one that I have uploaded. Good. Okay. So last time we have been writing the gradient descent in one dimension. So we had written the algorithm. Actually, there's even some extra stuff here. These two lines and this line here are not really part of the algorithm. They're just used to record the intermediate values. So there's a starting value as x0. And then, ignoring these two lines, we had decided to have a maximum number of steps. And at each step, we take x and we subtract the gradient, which in the one-dimensional case is just the derivative, multiplied by some step size, which we call alpha, and which is supposed to be some small number, where small means something different depending on the problem that you're trying to solve. So depending on f, here you can, I don't know, pick 0.01 or something. But you might want to adjust it depending on f and x0. And so you just iterate this a lot, and then you get the result here. And then we had stored the intermediate results in an array in which you insert the starting point, and then at each new step, we just recorded this. And we had a few example functions. Here, there's one which is a couple of lines which are supposed to plot g, and so you see them here. It's a quadratic function in this case, so it has, in the end, it has two local minima. One is the global one that you're looking for, and gradient descent is going to find one of these two, depending on where you start from and depending on the step size. If it's small enough and you have enough iterations, you'll get arbitrarily close to one of these 2 points, essentially. Okay, so this was the last time. Now, the other thing that we had been doing was thinking about computing gradients, actually derivatives, but we will generalize that to gradient automatically. And we were, I mean, when you have an analytic expression like this, you can compute the gradient analytically, but sometimes you don't, or it's just annoying to do it. So you can ask the computer to do it, and then there are several ways, and the one which we saw was finite differences, which, as we said, consists in simply taking the expression of the derivative and removing the limit and substituting this with a small delta x, a small delta, small shift in the position. And we also said that we cannot numerically take the limit, because as you reduce this delta and make it smaller and smaller, this gets, on the analytical side, this gets closer and closer to the analytical expression, the limit, which you would like to have this delta to be as small as possible. But at some point, numerical issues kick in, and loss of precision occurs, and therefore there's just going to be some balance between how small you can make the delta and how much precision you can retain. And the culprit of this precision loss was this difference here. Okay, the difference between two floating point numbers which are very, very close to each other. That's one classical, typical example of how floating point values lose precision. Okay? Okay, so this is all the summary about last time. Now we keep going from there. One easy thing that we can do immediately. Oh, by the way, in the code here, you might notice that with respect to the last lecture, I changed this. I don't know what I was thinking, really. I called that epsilon. I'm calling it delta because I want to use epsilon for something else. But that delta is just like a way more traditional name for this quantity. Okay, delta or delta x or whatever you want to call it. I'm calling it delta. All right, so having said that, well, we can just have a quick look again. Say the difference between the exact gradient of g, exact I mean analytical, at some point like 0.4 we were using as an example at some point, and then this gradient x at point 0.4 with the delta of 1 to the minus 5. Okay, let's use the default for delta, and you see that now you get to this level of precision in which, I mean, you make a small error, okay, in using this this numerical formula compared to the analytical one. Okay, so this is an approximation. But we can easily improve on the approximation, so this is kind of interesting thing to see. And the idea is sort of this. So here on the bottom right, you see the scheme of what we are doing, right? We were saying you have some function, which is the red one. You have some point x, which is here. You take a displacement x plus delta x, and then you just look at the change in the function value, the vertical one, and you just take the line passing through those 2 points, and the slope of that line gives you the derivative. Now, an easy way to improve on this, in general, is to do something like a centered, this is called the centered numerical derivative. I'm just going to maybe use a different color, like, I don't know, orange. And so instead of looking at x and x plus delta, you look at x plus delta and x minus delta. Okay, you look at this point here, and then you just take the, you can, sorry? It's, okay, thanks. Do let me know if it freezes, because of course I cannot see it. So, thanks. And basically, I mean, my drawing skills are horrible, as you know very well, but, well, no. Okay. Something like that. Anyway, so this here it has a very similar expression. It's just f of x minus delta, or plus delta, minus f of x minus delta x divided by 2 delta x. Okay? So it's just that. And sorry. This is muted. Can you still hear me from home? Yes, good, thanks. Okay, sorry, not sure what I did. Maybe I'll do this. So I accidentally pressed the key with the palm of my hand. Anyway, so we were saying this way of computing derivatives is, I mean, it's centered. It's centered around the point that you want to take the derivative on, and it's possible to prove that in general it gives better results. But we can see it live by just doing it. So you just write minus delta there and divide here by 2 times delta. And now I'm reloading the code. And if I recompute the same thing as before, you see, so now my derivative here has an error with respect to the analytical one of 10 to the minus 10. So it's 5 orders of magnitudes better than before. Okay, so it's a very big improvement in this sense. Good. So, okay, we'll use this instead. Now, before we move on, a couple of things. First thing is, this is not the only, and indeed not necessarily the best way to compute derivatives automatically. So the topic is, in general, is called automatic differentiation, for obvious reasons. And this one is just, let's say, the most straightforward way, the easiest one. It's sort of nearly a direct translation from the mathematical definition to the code. And with some approximation, it has also one drawback, as you can see, that you need to compute the function twice every time you want to compute the derivative, and computing the function in this case it's very, very cheap computationally, but in other cases it might be heavy just to compute the value of a function. And so doing it twice could be, I don't know, maybe not great. So there are other techniques which we'll not enter into in this course, but you should know that they exist. You can think of, they're also, it would take too long to explain, but you can think of that the basics work by essentially having a table of derivatives just like you would find at the end of a calculus book, like sine, what the derivative of sine, cosine, what the derivative of exponential x, what the derivative of log 1 over x. So a few basic functions, and then a few basic rules. The derivative of an addition is the addition of two derivatives. The derivatives of a multiplication is blah, blah, blah. And then, in general, when you have function applications, you have the chain rule. And it's all based on the chain rule. And so with the chain rule and a table essential of elementary basic derivatives, you can, in principle, if you think about it, you can do it just like you would do in a calculus course by doing it mechanically, essentially, right? Doing the derivative that way. It's slightly more complicated than that, and there are some aspects of, I mean, a lot of aspects of computational efficiency when you want to do that with a computer, and also computers can express somewhat more general functions. Let's say in a function in a computer you can have a for loop, which you generally don't have in a standard mathematical expression, or if conditionals, or things like that. And surprisingly enough, you can differentiate through those automatically with sort of the same technique. It's a vast topic, and it's quickly evolving because this is used a lot in machine learning, as we mentioned at some point. And so if you want to do automatic, I mean, nowadays in machine learning, automatic differentiation is the standard, it's the norm, and everybody uses it. And it's based not on this, but on other techniques, which are somewhat more advanced than this. But occasionally, you can still use this. And also, well, we'll come back to this at some point later today, or perhaps next time. Anyway, so this is it about automatic differentiation, sort of. One other thing that I want to point out, which I don't think has happened in this course yet, and it's the following. This grad function, you see, it takes some arguments, the first of which is another function, okay? I don't know, I mean, this is possible in Python and many other languages, but not all. In Python, this is possible because functions are so-called first-order objects in the first-class objects in the language. So in the Python language, functions can be treated just like any other value, just like you have a float. So for example, here, I can have, I don't know, g is a function. You see, you can ask for its type and so on. So and you can even assign things to that. I mean, I can create, if I want, I could create a list with functions, say, for example. Nothing stops me from doing that. This is in jargon, we say that they are first-class objects. This is not the norm in all languages, but this allows you to write functions that take other functions as arguments. These kind of functions that take other functions as arguments, are generally called higher-order functions. That's related to the underlying theory about these things, which was, I mean, it's related to terminology used in theoretical computer science, let's say, and it's related to lambda calculus. Did you hear about lambda calculus? Have you heard about that? At least heard that it exists? No one? Nobody has ever heard of lambda calculus. Well, historically, when the dawn of computer science, of theoretical computer science, you might have heard of Alan Turing at least, and Turing machines. Okay, Turing machines are a model of computations, and that allow to define universal Turing machine, which are a mathematical model for a computer, and on the mathematical model for a computer is the basis of what we use nowadays. And basically, any device that you have is, you can see it as a sort of an approximation of a Turing machine. In terms of its computational capabilities, the approximation consists in the fact that it doesn't have an infinite tape. It has a finite amount of memory. Apart from that, that's a straight translation in a sense, in many ways. Okay, if you completely ignore all the practicalities of the thing and you just look at the theory. Now, in parallel to the Turing developing his ideas, Alonzo Church developed an alternative set of ideas. Was Turing's, I think, mentor, PhD advisor, if I remember correctly. Anyway, they were also thinking about how to define mathematically computation and what's computable and so on and so forth. And he came up with something called lambda calculus. And it's quite interesting, but it's not very popular in terms of applying it in practice because of physical consideration, practical consideration, because it's way easier to implement in practice a Turing machine, essentially, than something based on lambda calculus. But it's, on the theoretical side, it's equally powerful. It's very fruitful in terms of, I mean, theorems that you can prove about that and concepts that you can define. And so that's a whole thing called lambda calculus, which gives the name to something which still exists in Python, which are called lambda functions. Okay, so lambda calculus is all based on higher order functions, so functions that take other functions as arguments. Okay, and these functions are so-called anonymous. So let me say this, maybe we'll speak about, so we are not going to get into lambda calculus. I just want to mention that historically that's where the name of the lambda functions in Python comes from, and it's related to these topics. But the topic I'm going to speak about is, well, two things, essentially. It's closures and lambda, or let me call them anonymous functions. Also called lambda functions, also called just colloquially lambdas. Or sorry. Okay, good. So in order to introduce this, okay, so all of these are very closely related topics to one another and related to this issue I was mentioning of the fact that you can have functions that take functions. Okay, so let's start. Maybe we can start from just observing in our particular code how this thing can come about, how these things can be useful. So let me save this. Let me save a copy of this as version 3 before I modify it. So I'm saving a copy and storing it there for later. And now, consider this. Suppose that I was trying to optimize, instead of the function g, suppose that I was trying to optimize this function k here. Now, if you look at the function, if you just plot it, you can observe it, and it looks similar to the one before. It has still two minima. One difference visually is that the global minimum is much flatter. I mean, there is a minimum here. You just not really see unless you see it now. You see that zooming in, you observe it at some point. But but this has a more complicated expression. And maybe, I mean, you could use the chain rule to compute the derivative of this, but maybe you don't want to. And so what you can do is, well, let's say now I have a way to compute derivatives automatically. Okay, so I could say def grad of k at some point x, well, I could just say return grad, my generic gradient function, of the function k at point x with a default delta. Let's just forget about delta for the moment. It's going to be good enough, right? And so now you can define the gradient like that, and after you've defined the gradient, then you can, I think I have here. Okay, so you can call, you see the minimizer, the gradient descent, on the function k, starting at 0.3, and now the gradient, our third argument, needs to be the gradient of the right function, right? And maybe, I don't know, restore the alpha here. This was alpha, and this was max t. Okay, now you can do that. You can check what happened by plotting plt.plot. Yeah, so this was the line that we used last time. So we have the intermediate values, and on top of those, we compute the value of the function and plot that. And you can see here. Oops, sorry, no. And you can see that it's kind of working, right? I mean, not sure if it actually reached the minimum. Apparently, I guess so. Looks like it, or at least very close. Anyway, so it worked. It worked because we now have the correct gradient. Now, here's the thing. For every, now, if you follow this procedure, every time you have a new function, you also have to write, you also need to write the new gradient, right? Because you need to pass that to this function. But this gradient here is just a particular realization of this function here. So let's look at this function here. This function here takes one argument, but uses two arguments here. Where does this k argument come from? It comes from, it's not one, so where does this k come from? It does not come from inside the argument list. It must come from outside the function, all right? Now, this is called a closure. A closure, as spelled here, closure, in a sense, it's a function that uses values from outside the function itself to do its computation. So it, one can say it captured the variable in a sense, and it closes around. That's, I think, the origin of the name. So it has captured this variable k, and now this variable k is used inside, and you don't see it when you call it. Okay? Good. So this is a closure. Now, the other thing is, as we were saying, that it's annoying that every time you have a function k or whatever, you need to write these couple of lines of code just in order to be able to use it inside the gradient descent, and maybe you don't care about those and that function grad k, maybe you don't care about it anymore, right? After you've done the minimization, what do you care about the derivative? Probably nothing. It's only useful as an intermediate computation for the gradient descent algorithm. So observe this. Okay, what did I write here? Do you know this? Does anybody know this? Seen it? Just one? Most people haven't seen this, have never seen it. Okay, so here, what I'm writing is an expression which, you see this lambda is written in blue, it's a keyword, it's a new keyword in Python. And then this, all of this thing is a function. It's a function without a name, so it's one of these anonymous functions. That's the definition of an anonymous function. So you can, let me comment this out. Lambda x like that. So for example, this here, you see, it's a function. It's a function of one argument, And what it does, it computes the square of its argument. But the function itself doesn't have a name. Okay, it's a value. Now, you can assign a name to that. Let's say SQ. You could say SQ is equal to this. Okay? Now, in that case, SQ is a function, just like G, just like H, just like everything else. It's a function, and you can compute, and you can use it to compute stuff. So here you see, instead of using def SQX something and then return X square, I just written everything in one line. But the important part here is that this part on the right is evaluated before the assignment. So first the function is created, and only later the name to the function is assigned. We can do the same with this. And this, so if I write grad k lambda, say for example, okay, now what's grad k lambda? Grad k lambda is a function of one argument that performs precisely the same, precisely the same thing as this function here. Okay? So here I have a function that, given an argument, calls this other function with the variable, with the function k and that argument that I gave. All right? Here, and then, and this comes with a name, with its own name. And so you see it here. Here I have exactly the same thing. And then I also gave it a name, and so I got the same result in the end. But I could, in principle, if I wanted to, I could keep this without any sort of name. And I could also, this is not generally done, but I could also do this. Take this function, define it on the fly, and put it in parentheses just so that it's one object, it's for precedent, and then I could even call the function on the argument. Okay? And so, what does this mean? It means that, oops, sorry. It means that in the end, when we run our algorithm, our gradient descent algorithm, you see in place of grad k, we could equally well write grad k lambda, because it's the same function. But we could even write just this. Okay, because when you write grad k, that, again, it's one of these higher order functions. When you write grad k there, the function graddesc receives a value as the third argument, which happens to be a function. And you can do it like this, grad k lambda, and you can even just, don't bother giving it a name. You can just write this here. Oh, sorry, not there. Well, I'll write it. Lambda x grad kx. Okay? And you see that the final value should be exactly the same as before. Okay, so here you see this one thing is a function without a name. It's also a closure. It's both. The important thing is that it's without a name because it's a lambda. It's also a closure because inside the function, just like this was a closure, as we said, this captured the k value from outside the function. It does not get through the argument. Here, as well, you see that this is an anonymous function, and it's also a closure because this value k here has been taken from the outside. Okay? Remember, I mean, pay attention to this fact also, that just like in any function, just like here, I could write whatever I wanted for the argument name, right? I mean, it's arbitrary. Okay, so this x here is the argument of the function, and it's not captured from the outside. Same here. You can write lambda xx, for example, like that, and you see this value, this name here is related to the function argument. And so the general rule about lambda functions in Python is the following. You write the keyword, then you write one or more arguments. You can write more arguments by using commas. So say, for example, lambda xy, if you want to have a function of two variables. And then you can say x squared plus y squared, for example. So the rule is you have one or more arguments without parentheses and separated by a comma, then a colon, then you don't go to a new line. Whatever you want to compute in Python must be a single expression, and that's what gets returned. And so this is what the function returns. All right? Pretty easy. If you want to have more complex computations that take several lines, in Python you just cannot do that. You're limited to one line of code, essentially. That's a limitation of Python itself. It's not. There's no reason for that particular reason except for syntax requirements of Python. Anyway, so this is a function of a couple of arguments. OK, so what can we do with this? Well, every time you call a function now, you don't need to bother necessarily writing this thing. So you can even take this thing here, comment it out. Whenever you have a new function, you know that in order to compute the gradient, you can do this. But I mean, this, we don't really even need to do it ourselves. We can let the computer use it as the default thing to do. So the idea would be my gradient, okay, f, is something, I'll give it a default value of none, whereas in many cases like this, none has the meaning it was not provided by the caller of the function. And now I say, OK, but if the gradient is none, if this is the case, then you know what? So if the user did not provide me with the gradient of the function that I'm trying to minimize, then I'll just compute it automatically. OK? Something like this. So you see what happens? If I provide the gradient like I did before, like I've been doing so far, if I do this, say, with G, we had originally G and then grad G, grad G. OK? So in this case, nothing changes compared to the previous case. But if I omit this argument, then this is going to be none. And then here, I'm going to hit this line where grad f is going to be a function which is defined by using this automatic differentiation engine, let's call it that, which takes the function that I gave, the one that I'm trying to minimize, and whatever the point is, whatever point I give it, it computes the gradient on that point, at that point. So you see, this has captured f, so it's a closure around f. And here, inside here, I gave it a name, inside here. And then I can use it here. So let's see if it actually works, and it does. OK? So this can get pretty confusing quite fast. So you should experiment with that. Do you have any questions about this? No? OK, so this is pretty useful, and it's actually very, very common to have something like this. Where's another case in which something like this is common? Well, one example could be that we are going to see it later, but one example could be something like that. Suppose that you have some function, I mean, I don't know, my func, OK, something that takes maybe an argument, and then maybe, I don't know, some parameters. OK? Suppose that you have a function that someone gave you, and it takes some argument, but also some parameters. OK? And now, suppose that you now know the value of the parameters, and you want to minimize the function with respect to just x. Suppose that. OK? A, B, and C are fixed. They are, I don't know, 1, 2, and 3, whatever the value is. They're fixed. But you want to find the x such that this whole thing is minimum. How do you do that? Well, you would like to take all this thing and give it to our optimizer, right? You want to take, I have a function to minimize. I want to take it and give it to the minimizer and let it give me the answer, right? Now, the fact is, our minimizer, if you look at it, it only takes a functions of one argument, essentially. The assumption of this is that this function is supposed to take just one argument. But here I have a function with 4 arguments. How do I do that? What can I do? I can use a lambda. So if you write this lambda, let's say xx, I'm just using the double x here just to clarify that this is a local argument to the lambda, okay? So you could have something like this. Okay, if you write something like this, now what comes out of this expression is a function of one argument. Okay, it's a function of just this xx. And the other arguments are fixed, all right? So there are questions. Could you please repeat what closures are? Okay. Closures are functions like this one, where some of the pieces, some of the values used in the computation comes from outside the body of the function. You see here, k comes from outside the body of the function. It's not part of the function itself. So that's a closure. Here, this is a function which uses f, and f does not come from inside the function, which is this. It comes from outside, namely here. So this is a closure, and this is a closure. Okay, another question. Since we also have f as a function argument, why couldn't we just pass grad as an argument and then write grad fx? Good. Okay, good. So that question there says, why can't we just do this? Okay? So if you do this, what happens? Suppose you have some function, g or k, doesn't matter, and then you write 0.3 and then grad. What happens then? Well, you see grad missing one positional argument. What happens? You give grad here, grad gets there. Now this line then is ignored. You get up to here, and you see that you are trying to compute a function over one argument, which is what I was actually talking about a moment ago. So here, this grad f must be a function of just a single argument. Otherwise, you get errors. In particular, if you try to use grad here, grad takes at least 2 arguments. You see, grad itself takes at least these 2 arguments. There's an optional one, but let's ignore it. You have at least 2 arguments. So you cannot call it like this. And so you need to, here, you must have a function of one argument. And the way you achieve that is by doing this, which is a way to fix one of the arguments of the function and just let the other one change, which is also the same thing that I was trying to explain here. When you have a function and you have fixed all the arguments except for one that you let change.
But we also have that.
I'm sorry?
We also have that in the gradient descent.
So why wouldn't you do this? Okay, good. So the question could then be, why don't you do this? Right?
I mean, you call gradient. Well, so grad f wouldn't be enough in this case. And the argument.
Yeah, I mean, we can also, I mean, let's do this. Forget about that. Okay?
Yeah.
I have f. I have my automatic differentiator.
Or the gradient f would be just calling the gradient anyway. And then
No, just a second. Okay. We could do this. Okay, what I just wrote. We could do this, but this always uses the automatic differentiation. So if you want to always use automatic differentiation, you can do that. But what if you have the analytical expression and you want to be precise? You want the option to be more precise. You want the option to maybe compute derivatives in a faster, better way for whatever reason. As we said, this method is a little approximate, and it's also not very computationally efficient. So maybe you want to be better at that. Maybe you know for your particular function that you're trying to minimize how to do that better. And so you want the option to give the gradient yourself. Okay? Good. So you cannot do this. You want here to have the gradient for the specific function. Okay? Okay? Now you want the gradient for that specific function f. But now you want to have both things, either the possibility to compute that automatically or to be provided by the user. So if you must be able to provide it by the user, you must have some argument here, because otherwise how would the user could ever do that? Okay, so you must have the argument. If you want to compute it automatically, then you want to use this grad function, but this grad function takes 2 arguments. And here, sorry, this was like that. This grad function takes 2 arguments. And here you need a function of 1 argument. So what do? You use a lambda to fix one of the 2 arguments. Sorry, I pressed the wrong key combination. You use the lambda to fix one of the 2 arguments and just let the other one change. And now this works.
So
yeah?
if the user doesn't give it normal gradient function 0 takes 2 arguments, and you're trying to make it a way that it only takes 1 argument.
Yes.
And if it is given, it already has 1 argument.
If it's given, then it's the problem of the user to provide a valid function which only takes 1 argument. Yeah, so then if you give it as an argument, then the user that provides it must provide something that makes sense.
So we try to make it a general case.
Yeah?
We try to generalize it.
Sorry?
We try to generalize it like if the user gives a function or not.
Yes.
So we wanted to make the function work in both cases.
Yes.
And the user.
Yes. So to repeat, maybe people at home haven't heard all of this, but I think you got most of it. In any case, the final remark was we are generalizing things such that the user has the option to provide the argument, the derivative or not. Okay. So there are other questions here. Is it just easier to implement, or is it also computationally efficient? I'm not sure what you mean. I mean, what's the subject of this question? So sorry if you can clarify. The lambda function, I meant. Well, it's not computationally efficient, not particularly, and it's not that it's just easy. I mean, it's just easier to implement compared to this, compared to just writing. And also, this is valid for one function. You could do it. You could write the function definition inside here instead of using a lambda if you wanted, but I wanted to demonstrate the use of a lambda because it's more general than just this particular case. So this one here is useless. There's no computational efficiency. But then why can't I just write grad f of gx? In class, they asked the same question. So, OK. OK, good. Yeah, good. So, good. So we were saying, yeah. So this is lambdas. This is our first encounter with lambda functions. And you can see they're pretty powerful. And let me repeat. Consider a function in which you have more arguments that you wanted to, where you want to optimize just one of the arguments and all the others are fixed. Then you do something like this. OK? You can have even fancier things, I suppose. But let's not get into that right now, because it's confusing enough as it is. Good. Sure. Save as version. Let me save version 4. What's the question?
So it's just a syntax thing. In Python, always need to have non-default arguments before given default arguments.
Yes. Yeah, the question is if all the default arguments must come after the non-default arguments, and the answer is yes, otherwise you wouldn't be able to tell which is which. OK. So yeah. So you see that's why I mean, at some point last time, someone said, well, why do we need f at all in this function? And this is one possible reason why. OK. This is why I wanted to have f here, even though in the whole gradient thing you don't even use it. Good. Final thing about this function, it's convergence. So, okay, so let's just improve a little bit on our code. Our code right now takes a fixed number of iterations. That could be very suboptimal because, of course, you could have too few iterations and then you don't reach the end, or you could have too many iterations and just waste time when the function has already reached the minimum. Essentially, all the gradients are zeros, and here nothing is being done. Okay, and you see it if you do this with 1,000 iterations. You can see if you now look at the intermediate values. Well, let's look at the last 100 values. I don't know. You see that basically we've been probably wasting a lot of computation in this case. Not a lot, but I don't know, some computation. Okay, how do we change that? We want to use a convergence criterion such that we want the function to detect automatically when the procedure has finished. Okay, so we'll keep giving it a maximum number of iterations, but we don't want it, I mean, we want to be sure not to go on maybe for forever, but especially if we happen to make a wrong assumption about the step size. You remember that when we had a step size which was too large, the function was flipping around. So in that case, it would never converge. So we still need to have some cutoff at some point. So we'll keep around that maximum iteration stuff. But we also want to say, well, if you have converged, essentially you can stop there. Now we've seen in the theory part that there are different options about how to detect convergence, right? You've seen that you can detect when the x changes a little, when the function changes a little, when the relative values of those two change a little. Now, what's the relative values of those two, the change in the f and with respect to the change in the x? It's basically the gradient. If the step is small in the x, it's basically the derivative, right? So let's just use, I mean, we computed the derivative, we have the derivative, and it makes sense to stop when the derivative, the gradient, is small, right? Because, I mean, when that is 0, essentially you're at the bottom, okay? Hopefully, at least. So our criterion is going to be that the gradient needs to, I mean, when the gradient is small enough. So what do? You first compute the gradient. So I'm going to cut it here. Okay, sorry. Spider has encountered an internal problem. Let's see. I don't know. Let's see if it still works. Okay, you know what? I'll save this and then restart Spider, I guess.
Does it make sense to say, like, if the last time value you get is the same, you can stop the function?
Yeah, but if the last, I mean, the question is, what if the last, what can we say if the last 10 values are the same? Yes, but if the last 2 values are the same, it's the same. You just need 2 values. It's sufficient. If the time.
You don't know if it's like a floating point or.
No, I mean, if your criterion is it's just the same, okay. If your criterion is the last 10 values are exactly the same, down to the last bit, then you just need 2 values. Then it's going to not change anymore. If you have some level of precision, then you might say, well, if 10 values are below that level of precision, that would make sense. We're going to make it simpler and just say 1 value is below that level of precision. Okay, so yeah, I mean, if define grad f as lambda xx grad, does it remain also in future function calls? Well, the question here is about, I guess, this. Does this one remember a future function call? If I define, I'm not sure. So if you see here, I've used this technique of using none instead of putting all of this here, so I did not do that. I did not do that, and the reason why I did not do that is precisely what was written in the question on the chat. Because if you do that, then this is only computed in the first function call, and the later function calls will use the same lambda even if you change f. So this is not a good. This is not right. Okay, you need to do this and then check if the argument is none later. Okay, this is because of the way Python works. So thanks for the question. Anyway, we were saying, yes, we were saying let's make this detect automatically whether it converges or not. So you compute the gradient. Now you apply the usual function, and here you say, well, maybe if the gradient is small enough, some epsilon, then stop. And what's epsilon? Well, it's going to be a convergence criterion, which, I don't know, we can make it 10 to the minus 8 or whatever, 10 to the minus 10, whatever you want. Okay? It depends. I mean, even 5, I guess 6, whatever, it's fine. Okay? 10 to the minus 6 is plenty precision, I guess. Okay? So you see, I just split this into 2 lines because later on I want to just check the value of the gradient. Now, do you see any problem with this? Let's try. Should we try? Maybe, let's see. I get this, x minimum. Okay, 0.38. Doesn't look great. XS. What happened here? What happened here? Yeah? Yeah, exactly. So remember that when I say p is smaller than some value, I mean the absolute value of p, okay, the magnitude, because the gradient could be positive or negative. So you want the absolute value of this. Otherwise, what happened was that the first computation went through, but then the gradient was negative. It said, OK, I'm done, because it's smaller than epsilon, which is a positive. Oh, sorry, abs p, not this. Okay, this one here. And so, OK, let's try this one. Now, x min looks right. XS is still, I mean, what happened here? Let's look at the last 100 values, perhaps. You see what happened? What happened was that the intermediate values that we had, so here, these ones, they were allocated here, assuming that we would go through the whole iterations. But at some point, we just get out. And so here, at some point, you see it's no longer a good way. I mean, these were all just not left there to the wrong. So what do we do about it? There are, okay, so there are a couple of ways which you could use. One could be to just say something like this, xx equal xs of k plus 1 or something. I mean, I don't think this is going to work fine. I mean, you could cut the array somehow, but I'm going to use an easier way. Sorry? They take the unique of the vector. I mean, just discard the repeated values. That's not a good way because I don't think, well, first of all, that's very computationally expensive because the unique, what do you want, how do you do that? You either put everything into a set, which is expensive, all the values in a set, and then you get them out and they're no longer in order. Or, sorry? NP dot unique. Yeah, but it's still expensive. It's still, I mean, computing the unique values is still overkill for this. Because the general algorithm for computing unique values is not, I mean, you need to go through everything, essentially compare everything to everything else, in a sense. So either you need to sort the values in advance, if they're numerical, or you need to use sets, or you need to use a lot of comparison. What we are going to do instead is just use lists. Go back to lists. So because I'm not going to need to do computations at least for a while here, I'm just going to say the axis append, because lists are nicer to work with, in a sense, when you need to change their size dynamically. And then only at the end, I convert all of it into an array. So this thing here should work. Let's see. You see? Now I gave it 1,000 iterations, but I just used 56 of those. I don't know. By the way, this is adaptive, so you've seen the other function, which had much flatter bottom, and therefore the gradient is much slower. So you see, with function g, which was the original quadratic, it took 56 iterations. With function k, it took 1,001 iteration, meaning what does it mean? That the length of the list is 1,001. It means it had not converged yet. So here, now, we could have two situations. Either we hit this break, meaning that we have converged, or we exhaust all the iterations that we gave, and then it didn't converge. So what do we do? Well, we have a new value, converged equal false. And here, before breaking, we say converged equal true. So we detect convergence now. And here we also return converged. And now we run the code. And now I can do this and say converged. And then I can look at converged and see that it did not converge. But if I give it more iterations, like 10,000, you see that it converged. And how many iterations did it take? 2,295, because it's very slow. Converging is very, very, very slow here at the bottom. Yes, in a second. Just wanted to demonstrate that because this bottom of the function is very, very flat, gradient descent is very, very slow in converging, at least with the step size that we gave. Maybe we could try to increase the step size, but then maybe we could run into errors. Who knows? Anyway, it's all trial and error at this stage, at least. So you see, you don't even see the points. The gradient is so small that, oh, there we go. Finally, we see the points. Okay? So they are very, very, very tiny increments, and so it takes lots of iterations. There was a question.
Yeah, sorry. So instead of building this function as a for loop, could we also build it as a while loop with the breaking condition being absent, b is less than x?
Yeah, so the question is, could we use a while loop instead of a for loop and have the breaking condition be abs p less than epsilon? Yes, absolutely. The way I wrote it here, I have a for loop because I have a fixed number of iterations, a maximum number of iterations. If you have a while loop, and you wouldn't have a maximum number of iterations, if you want to put a maximum number of iterations there, then you add a counter, and then a conditional says, if I went over that number of iterations, then break without, and let's say converge is equal to false, and then break. So you can write it in another way. I think this one is, I don't know, slightly simpler. Okay, can we just compare the rate of decrease from xk to xk plus 1? If it's below a certain threshold, will break. So the rate of decrease, yes. The rate of decrease, what is that? Is alpha times p, I suppose? I don't know what's the rate of decrease from x to x plus. Either that, or maybe you mean, okay, yes. Yes, well, we're almost doing that, except that we are doing that in a way which is independent of alpha. So now if you change the step size in this code here, it shouldn't make much of a difference as long as the step size is small enough, you should reach the same point. Whereas if you just had all of this with the step size included in the, so look at this, I'll show you. If I do alpha times p, and you run the code, now this one here is not, I think, is not going to change much. So x min and converged is going to be more or less the same, okay? But, and maybe, you know, length of the number of iteration, 1,400. So we stop earlier than before because now we have this extra factor of 0.01 here. So we went below the threshold before compared to the other code. Now, however, if I now do this and I want to use a very small alpha, look at this. Did this converge? Yes. What's x mean? It's horribly wrong. So you see this? Because my step size is so small, I immediately get below the threshold, convergence threshold, and I mistakenly detect convergence. So you don't really want this. Because without this, then I can use whatever alpha. I mean, this is going to take ages if I try to run this. But still, it would at least give the, I mean, it's not going to take ages. It's going to go through all the 10,000 iterations, I guess. Yes. So this, at least, it has correctly detected that it didn't converge in the required time. OK, so I hope this answers the question. OK, so basically, we are done with the one-dimensional thing. Are there any other questions? Ready to go to multiple dimensions? In, what, 20 minutes? 20 minutes from 1 dimension to 1,000. Save a copy as, yeah. Is there a question? In maximum? Ah, because it goes away from maximum. If you initialize it exactly at the maximum, then it stays there, the gradient is 0, but that's a very, very unlucky case. I mean, that's the idea. That the idea is that it could happen, but it will probably, I mean, it's unlikely. And as soon as, so maxima are unstable with respect to this algorithm. It's just like a ball on the top of a hill, of a very smooth hill. If the function is very, very flat, but it's flat at the hilltop, then yes, it could get stuck there. Also, one other thing that might happen is the following. It could very well happen. So things where, situations where this thing go wrong. If you have a function like this and you initialize your point precisely at the maximum and then you stay there, okay. That's something we don't, not too concerned about because it's unlucky. Then the other thing is probably what you were saying is something which is similar to the function that we've seen, but something like that, which is not exactly flat, but so the second derivative is so small that it almost looks flat. And that's an unfortunate case. I mean, there's not much that you can do about it except analyzing the thing and detecting this somehow. And that can be tricky. One other situation when this doesn't work very well at all is something like this. So you see, this is a position where the derivative is actually exactly 0, but it's not a minimum nor a maximum. And you start maybe from here, and you start going down, hopping, let's say, down here. And as you get near this value, as we've seen, the steps get smaller and smaller and smaller and smaller and smaller. So if your step size was, I mean, this can slow down things enormously. Eventually, if you zoom in this place, if you zoom in, and if you're patient enough, and if your convergence criterion is, let's say, strict enough, you're going to observe something like this. A small jump over probably. Okay, there are two things that can happen. Either it gets slowed down so much that it never crosses that point, or it slows down, but at some point, because the step size is finite, it could jump over the point and then start accelerating and continue and then eventually go through. Okay, so in the first case, you're screwed. I mean, there's nothing you can do. It just slows down and stops. The other case, it's extremely annoying. You could mistakenly detect convergence, but if you had a stricter criterion and waited in and were patient enough, you could go through, and then find a better value later on. And if I mean, the gradient could never be exactly 0 unless you're at exactly that point. So, but before that point is slightly non-zero. But it could be that if the gradient is non-zero and your step size is not 0, you jump on the little bit. Yes, exactly. Yeah. So, so if the epsilon is small enough, then you could observe it go through. Okay, and this situation actually does happen a lot in practice when you cannot plot the function, you don't know what you're doing. I mean, you don't know the function, you're just trying to find the minimum. You cannot do the. So yeah, this is actually a real problem. And these so-called saddle points are places where this precise algorithm slows down really a lot. One way to overcome this is to use momentum, which you've seen in the theory part. This is not a local minimum. No, exactly. No, that's the problem of this algorithm. That this algorithm can fail in this situation. It can fail because it never gets through, or it can fail because it just slows down so much that it becomes impractical. The one cure for this is using momentum, okay, which has some sort of inertia to the process. Yes? No, computationally, momentum. Okay, so you need to keep in memory the previous value of the gradient. It's not that expensive. I mean, yes, there's a way to only consider the previous value. I mean, in this case, you can even overwrite the previous value with the current. In the other case, you need to keep the previous values and then also the new value, and so it doubles the memory essentially. It's not that big of a deal, and it's worth it because of these situations, normally. Okay, many people normally use it. Also, it's slightly faster and so on. So, good, great. Any more questions? This was all very interesting. I should have mentioned it myself, but it's good that you brought this up. Any other questions? You can try. I mean, try by your own to define function with a something like that and see this happen. You can plot it. Other questions here? No. Okay. So, multidimensional. First, before we go to the multidimensional case, there's something that we need to say about the words, the terminology, because it gets confusing every time. We are going to speak about multidimensional, you've seen in the theory part, multidimensional optimization, okay? But we've also been speaking about multidimensional arrays, okay? Now, so in NumPy, they are called, the type is called ND array, which is short for n-dimensional array. Now, this use of the word dimension is different. They are the same word used in two different meanings. Okay, so keep this in mind. What is that? What does that mean? The use of the word dimensions. Okay, so in NumPy, you have one-dimensional means a vector, essentially. Two-dimensional means a matrix. Three-dimensional means some sort of cube of values. Maybe you can represent it this way. I don't know, something like that, all right? Okay, so this, in this context, dimensions equals the number of axes. You know that in NumPy there's this terminology to denote the directions in these tables that you can write as axes, axis 0, 1, 2, okay? So this is the number of axes. However, in calculus, you have one dimension, you mean something like f of x, it means a function, sorry, let me write it this way, a function that goes from R to R. When we are going to speak about two-dimensional later, we are going to speak about functions that go from R squared to R, and so on, okay? I mean, obviously, just the number of inputs. And so, in NumPy, when you translate that, you have f of x. In the first case, it means f of x with x, a float, probably, just like we did in our code, right? So if you consider this, then we said, okay, we were initially thinking, and when we were plotting it also, we were thinking of this function g as something that takes one floating point value and gives you another floating point value. And that's the one-dimensional case. In the n-dimensional case, you have r to the n to r, which means that you write a function f of x with, oh, sorry, before you have a floating point input and returning a float. Okay, now, when you want to go to the n-dimensional case, you will still write f of x, but what's x now? It's x numbers together that you write in a one-dimensional array. Okay? With x, a 1D array of length n, returning, what does it return? Okay, this, I just cannot, I'll fix them later, but now it stopped working. Okay, my tablet has just stopped. So in the n-dimensional case, the input is a one-dimensional array of length n. You see the source of confusion, it's always a one-dimensional thing, but the length here is the dimension in this context. And it returns R, I mean, it returns a float, just like before. Okay? Is it clear? Good. Okay, having said that, let's see. Okay, maybe I'll create a new folder called grad desk nd, I guess. Okay, and then, well, actually, no, this one, no. I want to, well, let's start with function examples, which I should actually have saved in the other thing, but in the other place. Maybe I'll save them inside, nope, inside here. Okay, so here I have just some function examples. We are just going to observe the case in which there are two dimensions, because that's the one that we can plot. Okay, no other reasons. just because I want to visualize the thing. And that's only possible essentially with this case, a function from R2 to R. Everything else becomes too messy, and at some point, when we go to the general case, we just cannot visualize things anymore. Now, you have a function g. As you can see, now I'm assuming that x is a vector of length 2. So I have x0, and I have x1. And this function is just a paraboloid, because it's just a polynomial of degree 2 with some mixed terms, x0 and x1. And the gradient now, interestingly, I guess, is no longer a derivative. It's the derivative with respect to the first variable and with respect to the second variable. And so you have the derivative is a two-dimensional thing, meaning, again, it's a one-dimensional array with 2 entries. Okay? And then there's another function that I don't care about, really. So you could load this code. And now another code that I want to use is run test v0. Okay, so run test v0. Let me also save this inside the other directory, which I should have done before. Anyway, so now you see I have these function examples, and we are going just to look at these two first. Now, how do you visualize something like that? Well, there's a code for doing that. Now, I gave you the code. I don't really ask for this course that you know how to do this yourselves. I mean, it's not a focus on the course. If you want to learn it, it's fine. I don't. In terms of the plotting capabilities that you should have by the end of the course, for me, it's sufficient that you can plot a one-dimensional thing, or I mean, that you can do plots in a plane. Okay, so but now you can have plots like this using contours, and what this shows is contour lines of the function. So these are just the lines at which the function takes a certain value. And you can actually see, I mean, this is a paraboloid. So at this point here in the middle that you don't really see, but you can imagine, there's the minimum. And then it looks like a bowl, but it's just slightly squished in one direction and rotated. Okay? So this is what you see here. If you want, you can even comment this out and uncomment these 4 lines here. And this shows you a 3-dimensional version. Now, you don't really see it well, but the bottom, you can even move it. You see the bottom here, there's a minimum there. And for the rest, it doesn't look much like a ball, but that's just an effect of the cuts of our plotting choice, of our plotting range. But more or less, you can see that if you look at it from one direction, there are all parabolas. And if you look at it, I mean, here you can also squish. If you look at from the sides, it's all parabolas. Okay, so this is a function that we might want to optimize. The other one could be this one here, k. This is another function, and here's another one, okay, which looks sort of like this. And I've just plotted it such that the minimum is in sight, and so we can look at it. So let's go back to G. Good. Now, what about optimizing this? Well, I'll create a new file. This new file, I'm going to save it with a name which inside the same directory, the same folder, I'm going to call this grad desc nd, n-dimensional gradient descent. Okay, now let me take this other function, the one-dimensional version, take all of this that we've written, paste it here, Okay, I'll save it. Now this is of course one-dimensional. I want to generalize it to multiple dimensions. So just grad desc. What's going to happen? Well, forget about automatic differentiation, which we will see next time. What's going to happen? What do we need to change here? Let's have a look. F is now going to be a function. So, I mean, not much different there. x0, our initial point, is no longer a value. It's going to be a vector. Okay? A vector of the size appropriate for the function f. Now, as I said, forget about the gradient right now. Let me just take it away. No, let me don't take it away. Just remove so I'm going to pass the gradient as well. Maximum number of iterations stays there. Alpha stays there. Epsilon, more or less the same. You still initialize the. Now this is going to be an operation between vectors, but you write it the same. This here is going to put a vector in a list, but that's fine, I guess. Now here at each iteration, the gradient is going to compute something about the gradient of f, assuming that the user gives the correct function. Everything works fine. Now what about this line here? You see p now, what's p? It's supposed to be a vector, right? The gradient is supposed to be a vector. A vector of what length? The vector, the length of p should be equal to what? To x, the length of x. So let's check that. I mean, just make sure. Okay? This makes sure that at least the function grad f that the user has given makes sense. But it's not necessary, just a sanity check. Okay, what about this? Now, x is a vector, alpha is a number, p is a vector. Alpha times p just works just fine, and it works exactly like you've seen in the theory part. Okay? And then, so this is going to compute a new vector and put it the old vector. So you see this line here, I don't need to touch it. This line here, I don't need to touch it. What about this one? P is now a vector. Can I take the absolute value of a vector? Yeah, the norm, right? The generalization of the absolute value in multiple dimensions is just the norm. So we need the norm. Now, you know that in NumPy, maybe you know that in NumPy there's a function called norm. But writing the norm is so simple that I want to just do it myself here. Norm of any value x is just what? Is np sum of x squared or something. One alternative way to do it is maybe this, or even this. Okay, whatever you want to use. I don't have NumPy here, so I did import NumPy as np, I guess. Okay, so all of these are equivalent as long as x is a vector. Ah, yeah, the square. Ah, yeah. Sorry, the square root. Thanks. The square root. Yeah, I mean, yeah, people does sometimes use the known square, but not in this context. So thank you for reminding me of take the square root. Good. Okay, so what else? I mean, this line here could be problematic. I don't know. We'll see. But basically, we are done. That's the n-dimensional version. Okay, so in the run test 0, okay, we'll finish this up next time. Let's just see it in action. Okay, so here in the optimization, I can do from grad desc nd import grad desc, and then grad desc of the function g, starting from the value, I don't know, what value could we give? np array, you know, maybe let's write x0 here as np array of, I don't know, 1.1 minus 1.0, 0.5, I don't know, something like that. Whatever, x0, and then grad g, and then let's leave everything else as default. And maybe do x min and xs and converged and do this. So write in the script. I'm not sure this is going to work. Let's see. It did run. Now x min is this. Okay, I found a minimum. At least I found a point. The xs, what's that? It's an array of coordinates, and I want to plot them now. Maybe I want to plot them in the contour plot. So I don't even need the function value. So let's run this. And then here I want to say plt.plot. And then I need the x and y's. So the x are all the first coordinate of the vector. So it's going to be x's of all the lines, just the column, x's of all the line, column number 1, and then maybe with the line, and maybe in blue, perhaps. There we go. Okay. You know, maybe do it this way. Good. So what happened here? We are done, basically. We'll finish up next time. What happened here? This is a starting point. As you can see, it moved somewhat. I mean, it need not go straight for the minimum. It moved in this direction, and then it curved. And it sort of, if you think about it in the three-dimensional case, it went down the steepest descent. So you remember that this was kind of a paraboloid which was squished on one side. It went down from the starting point towards basically the bottom of the valley, and then down towards the minimum along the narrow direction of the valley, something like that. Okay, you can have a look yourselves. Final thing, I think that you've at least mentioned, if not proved, I mean, maybe it's in your notes, that the direction of the steepest, the direction of the gradient is always orthogonal to the contour lines, right? Now look at this. These are the contour lines. The blue line shows you the direction of the gradient. Does it look orthogonal to you? Not really. Is math broken? Did we just... Yeah? Why? What's the problem here? No. I mean, this is a perfectly valid representation.
Yeah, but here it doesn't seem orthogonal.
Yes.
But when you like rotate this and look at from the starting point of...
Okay, you're almost there. So for those at home, your colleague said when it's orthogonal, but it doesn't look like it because it's rotated somehow. Well, you're almost there. It's not that it's rotated, it's that it's squished. Ah, sorry. Well, it's not. Yes, squished in one dimension. So if you look at the range, it's from -3 of 3. If you make this square, so this is tricky. If you try to make it square as you can, you see that it's actually, so okay, good, sorry, I didn't understand. You see that it actually goes through the contour lines orthogonally. And the contour lines, of course, change. At some point, it deviates. I don't think it even converged. No, you can give more iterations if you want, I guess. You run it, and now, there you go. Now it finally got to the end. Okay, there. Of course, one would like to do better than this. One would like to go straight for the minimum, but that's not entirely possible. And of course, I mean, we'll see better.
Maybe there is a way to syntax that the output is always on the scale.
Yeah, you can. Well, you can manipulate the aspect ratio of the plots with commands. Yes, instead of just doing it yourself with the mouse. Sure. Yes, good point. Okay, so I think time's up. I guess if there are no other questions, I'll upload the codes, of course, and stop the recording. See you next.